So in this section, we're going to be doing calculations involving KEQ and KP. We're also going to talk about something new called a Rice table. I would suggest strongly having your calculator out, doing the calculations that we do together, so that you can make sure that you're entering it in correctly and you're getting the same answers I am and you know where the numbers come from. So in example 1, I'm given a decomposition reaction. I've got N2O4 decomposing into 2NO2. Now I'm told that the Kp is 0.133, and I'm told that at equilibrium, my pressure of N2O4 is 2.71. So I want to find the pressure of NO2 at equilibrium. So I know that my Kp is equal to the pressure of my products raised to their coefficient over the pressure of my reactants raised to its coefficient, which is a 1. I know that my Kp is 0.133. I'm solving for the pressure of NO2, which I'm just going to make an x, and I know that that's squared, divided by N2O4 is 2.71. Now it's just basic algebra. All I have to do is solve for x. So 2.71, if I multiply both sides by it, I'm going to get 2.71 times 0.33, or 133, and I get that that's equal to 0.36043. Well, this is my x squared. I want just x. So I need to take the square root. If I solve for x, I find out that I've got 0.600 ATM. So if I'm given information, I'm given the KP or the KQ, it's really easy to just solve some basic algebra. But sometimes they don't give me all of the information I need to go straight there. So here, in example 2, I've got some information. I'm told that this is my reaction. I've got 0.298 moles of PCl3. I've got 8.70 times 10 to the third moles PCl5. And at equilibrium, I've got 2.0 times 10 to the negative third moles Cl2. So here's my problem. I know my concentrations of a couple things initially. I know the concentration of some things at equilibrium, but I don't know all things at equilibrium. So solving for KEQ is going to involve something called a Rice table. And this is going to be a skill that you need to know really, really well. We're going to do this here. We'll do it with precipitation reactions. We'll do it with acid-base reactions. We're going to do this a lot. Okay? So a Rice table, R-I-C-E. The R stands for my reaction. So I've got PCl5 changing into PCl3 plus Cl2. The I stands for initial. So initially, I've got 0.298 moles of PCl3. Now I want the concentration. I know that this is moles per 1 liter. So 0.298 divided by 1 is 0.298. So I've got 0.298 molar. And initially, I've got 8.70 times 10 to the negative third, again moles per liter, PCl5. Okay? I'm going to draw lines to separate all of my elements, and I'm going to draw lines to separate my letters. Okay? Now, initially, I have no Cl2. I'm told that at equilibrium, I have 2.0 times 10 to the third moles per liter Cl2. So if I went from 0 to 2.00 at equilibrium, then how much did it change? I had to add 2.00 times 10 to the third to get to 2.00. So initially I had 0. This is my change. This is what I have at equilibrium. Now, if I look at the change for the others, PCl3 and Cl2 is a 1-to-1 ratio. So if I'm adding 0.200 times 10 to the third Cl2, because it's 1-to-1, I'm also adding that same amount here. Now Cl2 and Cl5 are also 1-to-1. So this is also 2.00 times 10 to the third. However, if I'm making Cl2, then I'm getting rid of Cl5. So I'm going to take 0.298 plus 2.0 times 10 to the third, and I get 0.3 molar here. I'm going to take 8.70 times 10 to the negative third minus 2.0 times 10 to the negative third. And at this point, it's just simple KEQ. I know KEQ is the concentration of my products. So PCl3 is 0.3 raised to its coefficient, which is 1, times 2 times 10 to the third. Oh, that's a negative third, sorry. Okay, so then I'm going to divide by my reactants. So I had 0.0067 raised to its coefficient. So if I plug this all into my calculator, my KEQ is 0.0896. Again, I don't have units for my KEQ, so I'm good there. Okay? So the Rice tables are going to be super important. Reaction, initial concentration, change in concentration, equilibrium. Okay? Let's try another Rice table. Okay? So here I've got my reaction again. Okay? So carbon monoxide reacts with steam to produce carbon dioxide and hydrogen. At equilibrium, the constant, so my KEQ is 510. This time, I'm just figuring out the equilibrium concentrations of everything. And I'm told that I've got 1 mole of each component mixed in a 1 liter flask. So initially, I had 1 mole of this. I had 1 mole of this, 1 mole of this, and 1 mole of this. Okay? They're all 1 mole in 1 liter. So that's my concentration. My change, I don't know how much it's changing. So I'm going to say, since this is a reactant, I know it's going away, and I'm going to make it X. This one is also a reactant, so it's going to go away by some number X. This is a product. It's going to form. Now, instead of having a new variable, this is 1 to 1 to 1. So if this goes away by x, I would have x amount form. Same thing, 1 to 1 to 1 to 1. So if this went away by x, this will form by x. So I've got 1.00 minus x, 1.00 minus x, 1.00 plus x, 1.00 plus x. At equilibrium, I still don't know how much I have, but I know the KEQ is 510. So my KEQ is equal to the concentration of my products raised to the coefficient times the concentration of my products raised to the coefficient divided by my reactants raised to their coefficient. Whoops, this should be minus x. Now, because my numerator values are the same, I'm going to say that that's 1.00 plus x squared. Since my denominator is the same, I'm going to say that's 1.00 minus x squared. Well, I want to solve for x. So I'm going to say, since both of these are squared, I need to do the opposite. I need to take the square root of x. So 510 square root of that, or sorry, 5.10 square root of that, I get 2.26 is equal to 1.00 plus x divided by 1.00 minus x. Okay? Now, if I multiply both sides by the denominator, that'll go away. Now I need to distribute this through. So 1 times 2.26, I get 2.26. Negative x times 2.26, I get minus 2.26. X is equal to 1 plus x. Well, I want to get all of my numbers to one side. So what I'm going to do now is I'm going to subtract 1 from this side and 1 from this side. I need to get all of my x's on the same side, so I'm going to add that. Now, since I just have an x here, I know that that's actually 1x. So I've got 1.26 is equal to 3.26x. I need to get x all by myself, or itself. So x is equal to 0.387. Now, if I want to know my equilibrium concentrations, I have one more step. This number goes in for all of my x's. So my equilibrium concentration of CO was 1.00 minus 0.387, which is 0.613. This is the same thing for H2O, because it was 1 to 1, they're doing the same thing. CO2 is 1 plus X, so 1 plus 0.387. So same thing here. So these are my equilibrium concentrations for each of those. Okay? Rice tables aren't hard. The algebra is where people tend to mess up. So be really, really careful when you solve example 4. Now the one tricky thing in example 4, my molarity here, I was given moles for 1 liter. My molarity here, I'm given moles per 1.5 liters. So don't forget to calculate your molarity. Make sure you change your KEQ times 10 to the second instead of 102. This will take some time. Be patient. You're going to tell me how much of everything you have at equilibrium. Solve using your rice table.